Okay, so we're really happy to have Dino Rossegger here from Berkeley, and I guess you're in Berkeley right now, right?
Yes, I'm in Berkeley.
Okay.
I don't need you to pronounce the second affiliation. It's fine.
Oh, my German's a little rusty. I'm sorry, but he's here to speak on the structural complexity of models of arithmetic. So go ahead, Dino.
Yes, thank you very much, Atar. It's a pleasure to be here. I'm usually mostly invited into computability seminars, so it's especially nice to be invited to a seminar in some other topic. This is also a little bit of a warning. I tried to include as much as preliminaries as I could think of, but if there's something where you don't think you get what I'm talking about, please just interrupt me and I will try my best to explain it. So the talk is titled The Structural Complexity of Models of Arithmetic. So what do I mean by that? So the goal is to measure how complicated models of Peano arithmetic are structurally. So like intuitively, there's a few questions you could ask there. So for instance, how hard is it to identify elements of a model of PA? So usually up to automorphism, because you can't really do much more. But in my opinion, when I think about something, saying how complicated something is structurally, okay, I want to be able to identify the elements of a model. Another question I can ask is like, okay, that's very, very much related. How complicated is it to define an isomorphism? If I give you two models that are isomorphic, how complicated is it to define this isomorphism? Or I could ask, okay, like I give you a bunch of structures, and I give you one structure of these structures, and I tell you, okay, pick me out all of the isomorphic copies of it among all of these structures. So kind of like how complicated is the set of presentations of a model of PA? I should add here, I'm only talking about countable models here. So everything I'm doing is countable. It is like, even without like introducing any formal framework, it's easy to answer this for the standard model of arithmetic, just the natural numbers. I mean, how hard is it to identify elements of the standard model? Well, it's exactly those elements which are just kind of like the nth successor of the zero. So like I can identify all of these elements very easily, and like using these I can also easily define isomorphisms. But the interesting case, or at least what I've always found intriguing, is like when I thought about Peano arithmetic, I always had like the standard model in mind. Okay, it's very simple, and then I mean I didn't know a lot. I knew like Tenenbaum's theorem and a little bit stuff about like Scott sets, and I always thought, okay, well, the non-standard models, they need to be very complicated. So how complicated are they exactly? So that's basically the question that we want to answer here. So let us try to give a formal framework of actually how to quantify complicated in this sense. I don't know how familiar all of you are with like infinitary logic, but like most of what I'm talking about today is gonna play in like the playground of infinitary logic. So here's just some definitions for that. So you probably all know L omega 1 omega, and like you can put as kind of quantify complexity on these sentences, on the formulas in L omega 1 omega, by saying, okay, the sigma 0 formula are just like the finite quantifier free formulas. And then you go up through the transfinite by saying a formula is sigma alpha if it's an infinite disjunction of existentially quantified pi beta formulas for beta less than alpha. And you can say it's like a pi alpha formula if it's like an infinite conjunction of universally quantified sigma beta formulas for beta less than alpha. And so like L omega 1 omega is already like way more expressive than first order logic. For instance, you can write, I have like here this example, this one formula. If you let Pn denote the formal term for the nth prime in Pa and give any set in any subset of omega, then you can write down a formula which tells you, well, okay, and there is an element x that is divisible by all the primes by all the primes at Pn such that n is in x. and by no other standard primes. So basically, this is a sigma 3 formula, which already says that if A satisfies this formula, then X is in the Scott set of A. So you can already see, like, kind of like with relatively low quantified complexity, you can say quite a lot of things. And it turns out that you can say even much more things. In Scott's famous result from 63 already, he showed that every countable structure A has a Scott sentence. So that's a sentence in the infinitary logic L omega 1 omega, which characterizes this structure A up to isomorphism among countable structures. So every other structure which satisfies this sentence and is countable will be isomorphic to it. The proof of this result, well, at least all the proofs that I know, they rely heavily on the analysis of the so-called back and forth relations. Here's a definition of the like one definition of back and forth relations that we're going to use. This is due to Ash and Knight, so-called asymmetric back and forth relations. So you have given like a structure A, a structure B, and the tuple A in A and the tuple B in B, and you say that A is 0 below B, if all the atomic formulas true of B are true of A and vice versa. And then you kind of play like this back and forth game. So you're saying for non-zero gamma, AA is gamma below BB if for all beta less than gamma, and every extension D of the tuple B in B, there is an extension C of the tuple A in A, such that BBD is like beta below AAC. So you play this back and forth game. Originally, what was used in Scott's proof, I think, was like the symmetric version of this relation. We used the asymmetric version because we want to get like some kind of tighter bounds on the complexity. And like I think like since Scott proved his theorem, or like I think even before when Karp started studying these back and forth relations, they had like notions of rank. One attempt for this rank could be, for instance, the rank of a structure A is the least alpha, such that for every two tuples A, B, and A, if A is alpha less than B, then A is beta less than B for all beta be greater than alpha. So this implies like if A is alpha below B, then it must be then B is isomorphic to A or automorphic to A already. So this kind of assigned like an ordinal rank to the structure. But like, I mean, without telling you anything more now, it's not really obvious like what this rank means. Like, I mean, does this have any consequences, or is it just like some rank that is completely uninteresting? Already like, I guess like since then people knew that like there's a few things which follows from this kind of rank. But in order to like really like obtain I would say like a robust notion of a rank for a structure, it took like over 50 years.
Dino, I'm sorry, a quick question. So in this last definition, there is no mention of B. B can be anything, the capital B.
In the rank?
Right.
So basically, yes, that's very important. Thank you for pointing this out. This is very intrinsically only about A. And if I don't mention A and B here in these relations, this means that I have A on both sides. So like in my talk, I will often write like A is alpha below B without any mention to the structure. And when this is the case, then basically this means, okay, like I always mean like the structure A.
Okay, thanks.
So the rank is something very intrinsical about A. It just tells you how like the tuples in A relate to each other in some sense. Yes, so it took I guess like 50 years until we arrived at a notion of Scott rank which at least I would call robust. Montalban in 2015 showed the following theorem. He showed that if I give you a countable structure A and some ordinal alpha, then the following is equivalent. Every automorphism orbit of A is definable by a sigma alpha formula in L omega 1 omega without parameters. A has a pi alpha plus 1 Scott sentence. So basically this Scott sentence that A has is pi alpha plus 1 in this hierarchy. A is uniformly delta alpha categorical. So that's maybe a notion that you have not heard before. What the way I think about it is basically, because I'm a computability theorist, this means, okay, there is a Turing operator phi, then there is a real x, such as for every B and C isomorphic to A, if I feed this Turing operator x the alpha jump of the real coding C and B, then it will compute me an isomorphism between B and C. So this basically, this basically relates like the second question that I had in the beginning, where I said like, how hard is it to compute isomorphisms between two copies with picking out elements in a structure. So basically saying that like the automorphism orbits are sigma alpha definable gives me a handle on like how complicated it is to pick out elements. This is equivalent to the set of copies of A being pi alpha plus 1 in the Borel hierarchy on mod L on the set of structures in the language, on the topology of structures in the language. And this again is equivalent to no tuple in A is alpha free, which I will explain in a bit. And he said, okay, well, the least alpha for which a structure A satisfies all of these, or one of these, is what we call the parameterless Scott rank. There's also other forms of, there's also something he calls like the parameterized Scott rank. Here we will say parameterless Scott rank, and I will most often like kind of like just skip the parameterless and just call it the Scott rank of A. Let me also point out that like most results in this equivalence are not really that new. Like for instance, the equivalence between 2 and 4 is nothing more than the Lopez-Escobar theorem. It was known that I think that even like since Scott's proof that like 1 implies 2, but like a really, in my opinion, new and major thing of this theorem is that kind of like actually 2 implies 1 too. So 2 implies 1, because if you think about it, like 1 tells you something of like how complicated the structure is, like when you look at the structure, whereas while 2 and 4 basically tell you, okay, how complicated is it if I look at like a whole class of structures, how complicated is it to like pick out structures isomorphic to it? How complicated is the set of structures? So that's more of an exterior view. I will mention that like a lot of people are still not happy with this. They still think this is not robust enough. Although, I mean, I personally like it because it gives like this equivalence between these many different notions. For instance, like people in computable structure theory think a lot about like these categoricity things. But people have even defined something more fine-grained, saying that the Scott complexity of a structure, so this is still something more fine-grained, is the least complexity. And now you don't have an ordinal, but you have either sigma alpha, pi alpha, or d sigma alpha. So where they say, okay, well, I really want to know like what is the concrete complexity of the Scott sentence. I'm sorry, where d sigma alpha here means that's a sentence which is a conjunction of a sigma alpha and a pi alpha sentence. So it's a little bit more complicated than a sigma alpha sentence by itself normally. And this notion now is very robust if you like descriptive set theory, because it really corresponds to the Wage degree of the isomorphism class. But there's no need to think too much about it. Like for us, the important notion here is the Scott rank. Now, okay, if you look at this, then you will tell me, okay, Dino, you showed me all of this stuff about back and forth relations, but there's no back and forth relations here. Well, there are back and forth relations, namely in 5. So how are these connected? Well, they're connected in 2 ways. First of all, A, like A being alpha below B, means nothing else than that all of the pi alpha sentences true of A are true of B. Or equivalently, all of the sigma alpha sentences true of B are true of A. Or in other words, the pi alpha type of A is a subset of the pi alpha type of B, infinitary. We're always in infinitary here. So that's one connection. So if you think about just infinitary logic and back and forth relations. And the other connection now concretely to this theorem is this fifth point, which was alpha freeness. So which says that, well, okay, a tuple A is alpha free if for every beta less than alpha and every extension of A, there is an extension, there is A prime and B prime, such that AB is beta below A prime B prime. But this is not enough to actually witness already that A must be alpha below A prime, namely A is not alpha below A prime. So this sounds very technical and combinatorial. Like if you sit down with and like think about it for half an hour, like why this implies all the other things, it makes sense. I'm not gonna explain this now, but like, so if you remember here, we said like, okay, like all the automorphism orbits are sigma alpha definable if and only if no tuple is alpha free. And again, here, as Roman pointed out, like there's like no mention of A or B here. So this means like we're always like playing within the structure A, our back and forth games. Okay, so now if you think about Scott ranks of in some that can happen in some appear in some specific class of the structure, there's like an old notion by Mackay, the so-called Scott spectrum, which is just like the set of ordinals such that we have like a countable model of T with Scott rank alpha. I should say like every countable structure will have a countable Scott rank. That follows from Scott's theorem immediately. And there has been a lot of work in some classes of structures. So for instance, Esch in 1986, he characterized the back and forth relations in the class of well orderings. And if one looks at his work, one can see that, okay, that the Scott rank of the finite well ordering of size n, so like just n elements, is 1. The Scott rank of omega to the alpha is 2 alpha, and the Scott rank of omega to the alpha plus omega to the alpha is 2 alpha plus 1. So which means that the Scott spectrum of the linear orderings is all the possible ordinals, basically all ordinals below omega 1 except 0. Another thing I already said, okay, like the standard model of arithmetic is easy, and it is indeed easy. It has like the least possible Scott rank. It has Scott rank 1. Because if you think about how to define the automorphism orbits, well, I just need to write down basically this formula, which is even quantifier free. Like the nth element is definable by just n follows of the successor function. And 0. So 0 here, the dot means the formal term for 0. So we already know that 1 is in the Scott spectrum of PA. So what else can be in the Scott spectrum of PA? In order to understand this, our first idea was, okay, we need to understand the back and forth relations for models of PA. And well, when we started to do this, then we quickly realized this is not easy, because I mean I showed you like this sentence which defines like that something is in the Scott set. So even like with 3 quantifiers, you can already say that some set must be in the Scott set or not. And so we don't even understand the 2 back and forth relations so far. But what we can do is we have PA, so we have a lot of coding power. So we can try to formalize the back and forth relations inside of PA. So what I'm going to do is like, I'm going to use just like usual coding methods. So if you work a lot with PA, you will have seen this 100 times probably, like that you can code finite sets in PA, well, finite in the sense of the model, by using just the binary expansion. Just take the element 2 to the s for s in s. So like if you're in the standard model, then like everything you will be able to code are really going to be the finite sets, right? But like in your non-standard model, you will have like infinite numbers with like infinite binary expansion. So you will have like infinite sets. And like these, I can view like finite strings u, like just as an m finite set, like the counter pairing function of I and ui, I less than u. So it's important that these strings again are just finite from the point of view as of the model. So I like in my coding, I have like infinite strings in there. So using this, I can sort of formalize the back and forth relations by induction, saying that, okay, well, U, so U is now like kind of like this code. So U is 0 below V if for all X, the delta 1 formulas true about U are true about V. And of course, I need to be careful here because, well, first of all, I might have like non-standard formulas in here. Second of all, I could have that U and V are non-standard tuples, so they are like infinite tuples. And like in the back and forth relations, I only allow finite tuples. So in order for this to match up, I need to introduce like a new parameter here, A, which is kind of like the bound. So we call this the formal or the bounded back and forth relations. And then by induction, well, U is less n plus 1 A below V if for all X exists a Y such that the length of X is below A, the length of Y is below A, and UX is A and below VY. So it's just kind of like mirroring the definition of the back and forth relations, but with this extra parameter A here. And if I look at this, then this behaves as well as I could expect it to behave. So we can prove in PA that, well, for any tuples UV and for any AB, if A is less than B and U is B below V, U is N below V up to B, then U is also N below V up to A. And they are nested. So like if you're N plus 1 below, then you must be N below. So like this is kind of what you would expect for back and forth relations. So the main question is, well, okay, do they actually match up with the real back and forth relations? And well, they kind of do. So like if I take two tuples, then A is N below B if and only if for every real number M, every real finite number M models that A is like N below B with respect to the formal term for M. And furthermore, if I have like a non-standard element C, such that M is such that M models A is like N below B up to C, then A is really N below B. And so this is probably the best you can expect of this formal version. But it's also very helpful because this allows you to use overspill arguments and use elementarity and elementary embeddings. So using this, this is not very hard to show, but it's actually maybe the most important lemma in this talk, that A is omega below B if and only if the type of A is equal to the type of B. So that A is omega below B implies that the type of A must be the same as the type of B is quite clear, because A is omega below B if all the pi infinitary omega sentences true of A are true of B. And if I have any first order type, then I can just like take the conjunction of all the formulas in the type. That's a pi omega formula. So if every pi omega formula true of A is true of B, then the types must be the same. And for the other direction, we just said, okay, well, take two elements, A, B, which have the same type, go up to an elementary extension that is homogeneous, then they must be isomorphic, and then using that they are automorphic. Using that these two tuples are automorphic, there you can play with the formal back and forth relations. Basically, chase through the definitions of the formal back and forth relations, and then use overspill to go down to the original model. Yes. Yeah, so recall that, I mean, I just mentioned like in this quick like sketch of this proof that model M is homogeneous if every partial elementary map M is extendable to an automorphism. This already shows you, well, okay, if M is not homogeneous, then the Scott rank M must be greater than omega. Why is this? Because like if all of it has Scott rank omega if all of the automorphism orbits are definable by sigma omega formulas. But if it's not homogeneous, then there's two elements of the same type which are not automorphic. So same type, they're not automorphic. So in particular, the automorphism orbit of B cannot be definable by a sigma omega definable formula, because it's A less than omega B, which means that all the sigma omega formulas true of B are true of A. So if M is not a homogeneous model of PA, then its scattering must be larger than omega. And then abusing these back and forth relations, these formal back and forth relations and overspill arguments, you can get a lot of other results. The following result is, it does not use overspill. It's very easy. It's like if M is a homogeneous model, then the scattering of M must be less than omega plus 1. Why is that the case? Well, look how hard is it to define the automorphism orbits. You're homogeneous, so if you have the same type, then you're automorphic. Just like add up all the formulas in the type. So it's an infinitary conjunction of like unbounded formulas. So that's at most pi omega. In order to have scattering omega, you have to have a sigma omega definition, not a pi omega definition. But for homogeneous, we only get like pi omega in general. If, on the other hand, you look at atomic models, so so we call atomic means you are like you only realize the isolated types. So every type is isolated by a first order formula. Then you can have scattering omega, because then first of all you're homogeneous, and second of all the sigma omega definition is just like the isolating formula for the automorphism orbits. And what we get combining all of this is that, well, if you have any non-standard model M, so this shows that it is at most omega, then you of course have to see that if M is atomic, then you cannot be below omega. This again takes some work using overspill arguments and these formal back and forth relations. So combining all of these, we get that if you are a non-standard model, then as I intuitively thought, you should be quite complicated. Yes, your scattering must be larger than omega. In particular, like 1 and omega, so the interval between open interval between 1 and omega is not in the Scott spectrum of PA. It's disjoint from the Scott spectrum of PA. And if T is a completion of PA that does not have a standard model, then 1 is also not in the Scott spectrum of T. So far we know that the possible scatterings are 1 and omega plus 1. So what about the rest? I'm a computability theorist. So what do computability theorists do? Well, they reduce things, reduce one problem to the other. So in order to obtain a characterization of the possible scatterings, our first idea basically was to see if we can find some sort of reduction that preserves scatterings from linear orders to models of PA. So what kind of reduction are we looking for? So very recently, Harrison Trainer, Russell Miller, and Antonio Montalban, they gave like this definition of infinitary interpretability. So infinitary interpretability, if you're working in model theory, you know what it means to be interpretable for a structure to be interpretable in another structure. So this is basically the same thing, but with infinitary formulas. So we say a structure A with some relations P0, blah, blah, blah on it is infinitary interpretable in B if there is a sequence of infinitary formulas that define relations, the domain of A and B, an equivalence relation, and relation symbols for every other P0, for every other relation in A, such that, well, these relations, if I quotient them out and interpret them in B, like these formulas, it's isomorphic to A. So basically, this domain AB defines me the domain of A and B. this equivalence relations and equivalence relations that allows me to factor out afterwards. And Ri defines me the images of the relations in B on A. What is important here is basically this thing here, that I do not restrict my relations to have like some specific arity in B. So basically my relations are kind of can hold like tuples of any arity, which means that, okay, you might say, so no, but how can this be? Like if I talk about L omega 1 omega definability, like every L omega 1 omega definable formula only has like so many free variables. So this means that basically for every n, I have another formula defining this relation, and I look at the union of all of these sets, then this is going to be my domain A and B. And this very small distinction between n and less than omega seems to be very important, because this is what affords you a lot of power in this definition. So if you have this kind of like definable subset of B, which is isomorphic to A, then we say that A is infinitary interpretable in B. And if I can have like the formulas to be, if I can have like all the relations and everything is both sigma alpha and pi alpha definable, then I say that A is delta alpha definable in B. Now, this is very useful and already very complicated definition in some sense, but it does not really preserve you anything yet. In order to preserve you anything, we need something a little bit stronger. We need that A is in, we want, for instance, that the Scott rings are the same. So then we need that A is interpretable in B and B is interpretable in A. So this is what the notion of bi-interpretability tries to capture. So we have that A is interpretable in B, B is interpretable in A, and furthermore, if you look back, we had like these functions which induce the isomorphism between A and the interpretation of A and B. If I compose these two functions, the interpretation of B in A and the interpretation of A in B, then this composition needs to be somehow definable. Like if I am A, then I have a copy of B living inside of me. And in this copy of B, again, because A is interpretable in B, lives a copy of A. And this basically tells you that, well, okay, if I'm A, then I should be able to find this copy of this copy that lives inside of me, the copy of myself that lives inside of me. And the same must hold for B. And if all of this is true, and furthermore, if like I wrote it here at the bottom, if A and B are bi-interpretable by delta 1 formulas, and also like these two compositions are all delta 1 definable, then I can get, okay, the Scott rank of A is equal to the Scott rank of B. If that is not this case, if this is like delta omega for whatever, then the picture is not clear what exactly happens. But what I want to mention is there's like two very, very nice theorems on this bi-interpretability notion, which I want to mention. The first one, it's actually that nice that in the last talk I just put like the if-then direction and said that okay, this is clear anyway, for which I got like bad looks from Antonio in the audience, because it's actually an if and only if, and I think the if and only if makes this very strong. Namely that A and B, two structures A and B, are an infinitary bi-interpretable if and only if the automorphism groups are isomorphic by an isomorphism which is bare measurable, so it needs to be like kind of tame in the sense of descriptive set theory. And this is a very, very, I think this is a very nice result. And another result which is nice is that, okay, like I can think about like kind of like two structures being equivalent by saying, okay, well, they're like kind of this bi-interpretable, like one is interpretable in the other using infinitary logic. Or I can think about having a functor from the isomorphism class of one to the isomorphism class of other to the other, and then having a functor back that, and the two functors are joined anyway, but basically this result says that, okay, if you have an interpretation of A and B, then there is this is the case if and only if there is a functor which takes structures isomorphic to B and maps them to structures isomorphic to A, and also takes isomorphisms between two structures in B to isomorphisms in A. And these two operators which do these jobs are also quite tame. They're like in most delta alpha. So there's like kind of like these two nice connections, one with the automorphism groups and the other one that we have like two viewpoints. And I particularly like also the second one, because in my mind it's easier to think about a computational procedure of like, if I give you one structure, I produce another structure, instead of like thinking about like how can I write down formulas that interpret things in each other. Okay, and also the first theorem already like gives us a very good hint what to look at. Like if we look for an interpretation of linear orderings in PA, well, maybe we just need to look for some results which say that the automorphism groups are isomorphic. And it turns out that this is true, and this was proven by Geifmann in 1976. Namely, for any completion of PA and for any linear ordering L, there is a model NL of T such that the automorphism groups of NL are isomorphic to the automorphism group of L. So basically, we just looked through the book by Kosak and Schmerl, and we were like, okay, well, that seems like we can work with this. Like the theorem that if the automorphism groups are isomorphic, then usually you will have some kind of interpretation here. Seems like we can work with it. So let's look at this proof and see how complicated these interpretations are. So how does Geifmann's proof work? Well, Geifmann basically builds indiscernible sequences using some very special types. He so remember, a cut of a model M is a non-empty initial segment of M that is closed on a successor. N is an end extension if M elementary embeds into N, and M is a cut of N. And N is a minimal extension of M if there is no model in between. So if M is a if N is a proper elementary extension of M and there's no proper elementary extension in between those two models. And then Geifmann proved that, okay, if M is any model of PA, then M has a minimal end extension. And we can use this. How does he get like this minimal end extension? Well, he gets it by taking MA, which is basically the Skolem hull of M with a new element, A, which has type PX, where type PX is rather special in the sense that, okay, PX is indiscernible, which means if I take any subset of M and cannot see what I wrote here, and if I take any subset of M where all of the elements have type PX in the set, then the ordered if I take any subset of M, any two ordered sequences of this subset where every element has like type PX, then they must have the same type. The whole sequence. So like only the element, every single element in the tuple A has PX and B and TX, and the whole sequence must have the same type. And the type PX is unbounded, so there is no Skolem constant such that the formula X less or equal to C is in PX. And then if I do this, I get like this kind of minimal end extension. And then if I give you any linear ordering, and I give you the prime model of the theory T, then I can iterate doing these end extensions according to these linear orderings. So basically, I take the for any ordered tuple L1 to LL in L to the less than omega, I take like the extension NL1, then I take extension LL2, LLL, and then I union all of these up. So this construction gives us a functor that basically maps linear orderings to models of T. So as I said before, I don't like to think, a lot of times I don't really like to think about like interpretations, at least not at first when I start working with this. It's much more convenient to think of like, do I have a procedure which, given a linear ordering, gives me a model of PA? And this is exactly what this is. I give you a linear ordering, give me a linear ordering, give me a theory, and give me the type, and I will produce you a model. Like if I have the theory and the type and the linear ordering, then this is even recursive. As I said here, the functor is computable relative to t. And by the result before, this is equivalent to having that for any L, NL is delta 1 interpretable in L. Oh, this is nice, because if I would get that they're bi-interpretable, then I would get that the scattering of A is the same as the scattering of B, which, well, unfortunately, this cannot be, because we've shown that you cannot have scattering n for n greater than 1 as a model of PA, but there are linear orderings with this scattering. So in some sense, it is easy to go from L to NL, but it should be difficult to go back from NL to L. So how difficult exactly is it? Well, okay, how can we recover the linear ordering L if we have NL? So for this, we need to consider this equivalence relation, which is called the gap. So if I take any model of PA and then I look at the set of definable functions, which are non-decreasing and order preserving, then for any element A of M, the gap of A is the smallest set S, such that if with AS, such that first of all, okay, A must be in the set, and then if B is in the set, then basically I close under the intervals that these functions give me. So if B is less than FB for some function F in this big among all the definable functions, then X is also in the gap. And if X is less than B less than Fx, then also I need to add X to the set S. So this gives me kind of like, this partitions my model into intervals, into the gaps. And I can define an equivalence relation by saying A is gap equivalent to B if A is in the same gap as B. And then Geifman showed that, well, if A is in the gap of B and A and B both realize the same minimal type, then A is equal to B. So in every gap, there's at most one element satisfying a certain minimal type. And if I take the quotient of NL of the model, according with the gap relation, then this thing is going to be order isomorphic to 1 plus L. So why is this 1 here? This 1 is here because, well, I started with the minimal, with the prime model, and basically the elements of the prime model will be like kind of like this first gap, which is always here. And then afterwards I add the linear ordering. So I add like gaps for every element in the linear ordering. So if we look at this now, we realize, okay, this is nice. We can actually interpret L in an L using the following interpretation, just saying that, okay, A is in the domain of ln of L in an L if the type of A is equal to Px. So basically, the domain is all the elements satisfying the minimal types. The equivalence relation is just equality, and now the order is just the order on the model NL. So this gives me an interpretation, and it's not hard to see that now, because of Geifman's result, that the interpreted structure is isomorphic to L. Because now I basically threw away the first gap. And this gives me an interpretation. And this interpretation is, unfortunately, it's not delta omega, it's delta omega plus 1, because here I have a pi in omega formula. This is not sigma omega definable, unfortunately. So to sum up, we have that NL is delta 1 interpretable in L. L is delta omega plus 1 interpretable in L, which immediately means that, I mean, not immediately, you have to check like that these two functions are definable and stuff. But this means that L and NL are delta omega plus 1 bi-interpretable. But this interpretation is somehow weird, because one direction of the interpretation is very easy, and the other direction is very hard. And we thought that at first, like, okay, like, why is this like this? And we then proved, okay, well, this interpretation does exactly what it wants, what we want. It like preserves Scott rings and everything. But why? What is the reason that it preserves the Scott rings? Like, why is this weird interpretation? Why does it look like this, and why does it behave like this? And first, we like played around with special properties of arithmetic. But then we realized that we actually don't need to do this, because it is true that NL is delta 1 interpretable in L, but we can actually interpret way more about NL in L instead of only the basic relations. We can do the following. And for this, I'm going to need another definition, I'm sorry. So, okay, given any type Px that consists of formals in some class gamma, for instance, it could be an infinitary type of class pi alpha. We say that this type is sharply realized in some class K if there's a structure A and A in and a tuple A in A, such that the type P is exactly the type of A restricted to the class gamma. So in our case, what we're going to do is, like, we're going to use this in this definition. We're going to say, okay, let A be a structure in whatever vocabulary and list all of the sharply realized pi alpha types. So basically just look at all the tuples, look at all the pi alpha formulas the tuples realize, and these are kind of like these types that you add. Because now what you do is you define the canonical structural alpha jump to be the structure obtained by adding relation symbols for each of this type. And you interpret them by saying, okay, A is in the IF relation if A has like the type PI. So where basically this just says like it's the infinitary conjunctions of all the formulas phi in the type PI. And then one can show that well, for non-zero alpha beta less than omega 1, if the structural alpha jump is if A is beta below B in the structural alpha jump, then A is alpha plus beta below in the original structure B, and vice versa. So in particular, it preserves Scott rings in the sense that if the Scott ring of A is alpha plus beta, if and only if the Scott ring of A is beta. There is some if and only if the Scott ring of A subscript alpha is beta. So here there's like the structural jump missing. Now, I told you before, like this kind of like the most important lemma of like this whole work is that A is alpha below B is like that in models of arithmetic, A is omega below B if and only if they have the same types. And if you think about like how, if I give you a linear ordering, I give you the theory and I give you the minimal type and you produce me the model of arithmetic, then you're actually able to not only produce like the basic functions and relation symbols and everything times plus of the model, but you're actually able to produce relations which hold exactly of the elements of the same type. So in particular, what you get is you get that L, you get that N of L, the alpha jump of NL is delta 1 interpretable in L. And now combining everything, you get, we got that NL is delta 1 interpretable in L. Now we got something even better. We got that NL alpha is 1 interpretable in L. And we had that L is like delta omega plus 1 interpretable in NL. But like this delta omega plus 1 interpretation, like all of these formulas of complexity delta omega plus 1, like if I'm in the alpha structural jump, then the complexity of this formula just goes down to delta 1. So in the end, we get that L and NL alpha are delta 1 bi-interpretable. And I've said before, if we have delta 1 bi-interpretability, then we're golden. Then we know that the Scott rings are the same. But of course, unfortunately, not the scattering of L and NL are the same, or like fortunately, the scattering of L and NL alpha are the same. So we have to, not NL alpha, sorry, this should be NL omega here. NL omega are the same, L and NL omega. So we always have to add omega to every scattering to get the scattering of the model. And we've seen that linear orderings can have every scattering. So the models NL, if L has scattering alpha, then NL is going to have scattering omega plus alpha, which yields that for any completion T of PA, the Scott spectrum of T. Okay, this is not true. Well, for PA, the Scott spectrum of PA is 1 union alpha, omega less than alpha, omega 1. For true arithmetic, the Scott spectrum is the same, 1 plus this. For any other completion of PA, it's going to be just the right side without the 1, because you don't have a model of scattering 1. And then finally, this work also like led us to some more results about structural jumps. Maybe we were looking at this and then we were saying, okay, there should be something that's generally doable here. And it's true that, okay, A is delta 1 bi-interpretable with like the alpha of jump of B, if and only if A is infinitary bi-interpretable with B, where you have like exactly this weird bi-interpretation that we had before. Namely that one side, namely that B is interpretable in A, is very easy. It's like delta 1. And the other side is complicated. It's delta alpha plus 1. So this is kind of like, and this is actually just something we like realized in the last few weeks, that this is something general we can extract from this proof. And I guess that's the end of my talk. Thank you very much. Just to summarize, so these are basically the results of about PA. So the Scott spectrum of PA is 1 union all the possible or all the countable ordinals bigger than omega. If M is non-homogeneous, then the scattering of M needs to be less than greater than omega plus 1. If M is non-standard atomic, then we know it has scattering omega. If M is non-standard homogeneous, and this is something where I'm not yet happy with the result, is that then the scattering of M is either omega or omega plus 1. So I would like to know if like M is homogeneous and not atomic, does it always have to have scattering omega plus 1? I conjecture that this is the case, but I don't quite see the proof yet. And I guess like this last fifth point, I didn't even mention it. It's like for the computability theorists among us, like if you take any completion T of PA, you can find a model M, which is what we call high scattering. So it has like like if you look at only the computable models, then the highest scattering they can obtain is omega 1 ck plus 1. So here, if you look at all the T computable models, then the highest scattering that would be obtainable for everything that's T computable is the scattering omega 1 relative to T plus 1. And there is actually a model of PA which obtains that. Thank you.
Okay, thank you, Dino. And let's also thank our speaker. And if there are any questions, we have plenty of time. So go ahead.
Yeah, I have a question. Do these results also hold for parameterized Scott rank?
So the parameterized Scott rank is always, I guess, at most off by 1 or by 2. So you could replace this by parameterized Scott rank and get something slightly off, but you would still get something very similar. I mean, these results basically, like I don't know if you refer to like this result here, then this even holds for Scott complexity if you look at it. Like if you have if like A has a pi alpha Scott sentence, then pi alpha plus beta Scott sentence, then the alpha jump needs to have a pi beta Scott sentence.
I guess my question is more for that it could have every single Scott rank, if that would still be true for parameterized Scott rank, or if there'd be a few missing in there.
I think, I mean, I guess probably what would happen is like the omega would turn to omega plus 1 or something, maybe, because like there could be some, could be some shift there. I don't know, but I mean that would have nothing to do with like something specific going on here in the theory of in PA. It would be just something with like the gaps that you get when you look at parameterized and parameter-less scattering. So it would simply be like a scattering thing.
Do you have examples of homogeneous models where the Scott rank is exactly omega plus 1?
No, I mean, to be honest, I have not really played enough with them yet to really say anything. I think it would be very interesting to find some. I mean, I also believe that okay, like if you're not atomic, but I don't even have any examples now.
I mean, a guess of something to look at is the recursively saturated models.
Yes, precisely. I guess that is what you want to work with in PA. And I mean, I just played around a little bit with it, but so honestly, like I mean, before this project, like my knowledge about models of PA was very low, and I'm slowly catching up to this. And I mean, there's so much stuff about recursively saturated models that at this point I cannot say that I have really like checked everything yet that could be done there. So I'm pretty certain you could do something with like recursively saturated there.
Vague question. What?
Yeah, a
what
small comment that I would have to all of this. That, sorry.
Sorry, hold on, Roman.
Yeah, right.
Let's have Ken get in.
Yeah. My sort of takeaway is that what is so special about PA in all this? I mean,
that was actually my question too.
So I think what is special about PA in all of this, I think. Well, it's not surprising that for instance, that you can have like unbounded scattering. What is special in PA about all of this is I think like this lower bound of omega. I mean, that's for me the more interesting case is the most interesting thing is basically that you cannot have anything between 1 and omega. And what is special in PA about is, I mean, okay, why did we start thinking about PA? Simply because it's very, I mean, we were thinking, okay, about like, if we want to look like what are the possible scatterings in like some theories, like what's the most natural theory to start? Well, it's, I mean, to me at least, it's PA. I'm no set theorist, so I'm not going to start with ZFC or something. And I guess so. And I think like the most interesting part here is that you cannot have like these kind of like easy models that have like scattering n or something. That you're either scattering 1 or you have to go up to scattering omega, to scattering higher than omega. And I don't know, I have a good answer. What else is special about PA?
I could try, you know, because what I was going to say that in the theorem now, the first part of it, this Scott spectrum of PA, it really should be a Scott spectrum of GA would be for Geifman arithmetic, because everything you want to do eventually boils down to existence of those minimal types in indiscernible sets, and it all works beautifully for PA, but never works for anything weaker. So there is like this very special feature that allows you to do those interpretations there. So, you know, and those Geifman models are really linear ordering that are sort of puffed up, you know, around adding this sort of arithmetic structure around them. So it would be very interesting to take a look at things like Pressburger. I don't know if anyone, and whether you can have a finite number in the Scott spectrum of Pressburger, maybe Dave knows. But those are simpler, right? Presumably a bit simpler.
I think actually Jason is actually working on this, if I'm not mistaken.
Yeah.
Oh, I
so
see.
you
Okay,
do
so
get-
we'll see what it is.
Yeah, you do get that. You can get every Scott rank for Pressburger.
Every? I see.
Yeah, just by embedding linear orders essentially.
Specifically, Jason has gotten it.
Yeah,
Oh, I
this is Jason's
see,
result.
because there are some very simple models of Pressburger, like copies of Q and something like that, right?
Right,
I
exactly.
see.
That's really nice.
Yeah, so I guess you're right. So I mean, yes, you're right. I have like the same feeling that like Peano arithmetic is like somehow special type of like kind of having a minimality condition here. Like kind of, if you take anything simpler, then you probably won't get such a behavior. But yeah, something like that.
Do you know any other situations where you have the delta one interpretation in one direction and a bi-interpretation, but the other direction is delta omega plus one or something like that again?
I actually think this happens quite a lot. So I actually believe it happens to you in your work with like these fields. I mean, I would have to look at this, but you mentioned you have like this. I think when I was at your talk in Cornell, you mentioned this talk where you have to add a predicate.
Right.
And then you are like effectively bi-interpretable with the predicate. And now I think that very probably like adding this predicate already gives you the structural jump.
Okay.
And it seems to happen. I think like Antonio has like this book, like in his book within the arithmetic, he has like a chapter on like the first structural jump. And there he has some examples of some theories where he adds like a specific predicate and gets like this structural jump. And I think if I recall correctly, there are some examples of like reductions where this seems to happen. That you get like a reduction from linear orderings to something with this predicate added.
Okay.
I believe that this happens more often than we realize in computable structure theory.
Okay, yeah. I mean, I'm trying to think. The predicate that I added in that talk in Cornell was definable by an infinitary sigma 1 per pi 1, whichever formula. So I wouldn't have guessed that it gives you, delta omega plus 1 interpretation.
Oh no, so not delta omega plus 1. In your case, it would be delta 1, right?
Or delta 2 maybe, or something like that.
Yeah. So I think like in your case, it would have been like you have like delta 1 in one direction, delta 2 in the other.
Yeah. Oh, and the predicate evens it up. Yeah.
So in our case, it's like the omega. In our case, it's like you look at the omega structural jump. You would only look at the one structural jump.
Oh, okay. Right.
So I think like the one structural jump happens a lot. I have not seen any results where people actually like give like delta omega presentations.
Yeah. I mean, I was thinking here about delta 1 in one direction and delta omega or more in the other direction, because that seems like it might have something to do with the gap that you're talking about, the thing that's special about PA.
Precisely, it's precisely the issue is that like this kind of gap relations is that you need like kind of like if you have like an interpretation, you always have like kind of like an equivalence relation. And I kind of like threw away the equivalence relation by using these minimal types in the definition of the domain. But the problem a lot of times seems to be that you have to be able to define like this equivalence relation, and this is not easier to define than sigma omega, I guess.
No.
Any other questions? Okay, let's thank Dino again.
Yeah, thank you very much for having me.
Well, thank you.
It was a pleasure.
We appreciate you doing this while
Thank
while
you.
sick. So we hope you feel better soon.
Thank you.